Good morning, good afternoon, good evening, good night, good middle of the night, whatever time it happens to be by you as you're watching this. We're going to go over in today's notes what I'm calling Boundary Layer Physics Part 2. So kind of the extension of this concept of boundary layers that we talked about last time. We'll dive a little bit more into the math, just to review a little bit where we were last time, if it was been a little bit since you watched the video. Sorry for the craziness on this computer. So we looked at the physical laws that govern a boundary layer: conservation of mass, conservation of energy, Newton's second law, fluid properties, different things about gases and liquids. And then we started looking at this simplified case. So we had the simplest flow, the simplest geometry, the simplest possible fluid. We looked at a system like this where the boundary layer is growing over time, flow over a 2D flat plate. Looked at this property here called the Prandtl number, and then made a few other simplifications here and here about what we know in the boundary layer. So what we're going to talk about today is really the math behind the boundary layer. And what we'll see is by looking at some of this math, we'll be trying to kind of tease out the important quantities that we'll use later on in order to build models around convection. So that's really what we're looking at. We're looking at trying to tease out from the math what's important so that we could use that to build a model. We'll start kind of in the next lecture, the next video, I guess, diving into some of that. But this is going to be a little bit of math. We won't actually go through solving very much, but looking at some of these equations to see what factors are important and why. So as I said previously, we can think about conduction in a fluid or convection in a fluid really as conduction at the surface. Because the fluid is stopped at the surface, convection really is conduction through that first initial boundary layer. We can model that by the thermal conductivity of the fluid, the temperature gradient at the surface. So this is conduction in the fluid. That is actually what's going on. How we've been modeling it previously is something like this, right? So this is kind of our previous convection model or convection equation. If we take this, we had a little practice with this thing called non-dimensionalization before. We're going to continue to do that, and that will help us tease out kind of the key groupings of variables, like length and temperature and thermal conductivity and heat capacity. There will be kind of certain groups of these variables that are important. So if we look at the length scale, there's going to be a characteristic length L, right? That would be in this flow along a 2D plate. That's maybe the length of the plate. So we can non-dimensionalize the position along that plate. Basically, this is like percent along our plate. So it's going to be some number from, or fraction, I guess not percent. This would be like the fraction along our plate, somewhere between 0 and 1. And that's really what we're trying to do when we're non-dimensionalizing it. We're trying to turn things into something like that, like a fraction along the plate. We'll do the same thing with temperature, kind of as we've done before, defining a non-dimensional temperature. We'll call it T star. I think we've previously called this theta star. it doesn't particularly matter how we define the variables. If we plug these guys in, right, we can use these top equations here and here and just rearrange them to solve for t and y. And then everywhere in this equation at the top, everywhere where we saw t, we can plug in now this new t. We can plug in this right-hand side. Everywhere we saw a y, we can plug in that right-hand side. So that's what we're doing down here. We're just plugging in for t and y. If we rearrange a little bit, we can get to this form of the equation here. And you'll notice the right-hand side of this equation, that HL over K, it looks like a BO number. It's not a BO number. We define this as the Nusselt. It's a fun one to say. The Nusselt number. We give it the abbreviation NU. So a lot of our dimensionless groups will have just be named after the person who came up with them. That's how you really know you've made it in fluid mechanics or heat transfer. You have a non-dimensional group named after you. But the Nusselt number here, it's like a BO number. It's not exactly a BO number, right? So Nusselt is not BO, right? The BO describes temperature gradients in solids. That's where they differ. So the Nusselt number describes the temperature gradient in the boundary layer, or in our fluid. So that's where they differ. The BO number is talking about the solids. The Nusselt number is talking about this, the temperature gradient in the liquid. And it's at a given point on the surface. So we know from our some of the things that we've talked about already with boundary layers, the boundary layer is going to be, or the temperature gradient is going to be changing as we go along the surface from the left side to the right side. So the Nusselt number is going to be changing as we go along the surface. So it's a function of both Reynolds number and the Prandtl number. And right, the Reynolds number changes with x. So the Nusselt number is also going to be a function of x. So this is a function of x. So because the Reynolds number is a function of x. That's describing heat transfer. We can do kind of the same thing for fluid friction. If you take fluid mechanics, the shear stress at a surface, right? This is the shear stress. Sorry about my dog barking. I don't know if you heard that, but my dog is just barking at probably nothing. He's blind, so he often barks at nothing. Okay, so where were we? This is the shear stress at the surface. And this is what we would call Newton's law of viscosity. This is the viscosity here, and this is the velocity gradient. So you can see it looks a lot like the equation that we just wrote. We can non-dimensionalize this equation as well. We're going to become experts at non-dimensionalizing. We just kind of go and non-dimensionalize everything. Right? We can non-dimensionalize velocity by a characteristic velocity, typically the free stream velocity. Non-dimensionalize position the same way we did before with our characteristic length. Plug those guys into the equation. We would get something like this. And then we can define for external flow a friction coefficient, CF, this way. And what we find is that CF equals 2 over the Reynolds number times the velocity gradient. Right, the Reynolds number is a unitless number. U star, Y star, both unitless. So this is now, the friction coefficient is also a unitless number, or a dimensionless number. So that's really what we're trying to do, is we're trying to build up all of these different dimensionless numbers. CF describes the velocity gradient at the surface. Okay, so we have these two things, the friction coefficient, which talks about the velocity gradient, and the Nusselt number, which talks about the temperature gradient. We're going to be in this class more interested in the Nusselt number because we're more interested in the heat transfer aspects, things like temperature gradient, than the friction aspects. Okay, so what's happening? If we look at the fluid flow, we could develop different ways of looking at our physical laws, conservation of mass, F equals ma, and conservation of energy by a control volume analysis. To look at their laws, right? Little plug for fluids. Take fluids if you're not already in it, haven't already taken it. Yikes. That's what we do a lot in fluids. We've also done that some here in heat transfer for basically the same methods that we used to get the heat diffusion equation. Okay. If we simplify these equations, as we've kind of talked about before, saying the main assumption that we're making is that things are changing. Things like temperature are changing more in the y direction than they are in the x direction, or changing faster in y than x, so that the y derivatives are going to be big compared to the x derivatives. We can simplify this and get these three equations. So we can get a two-dimensional conservation of mass. We can get a two-dimensional F equals ma. Right, this would be Navier-Stokes. This is our continuity equation, if you remember either of those from fluids. And then we don't do this in fluids, but we could do the first law in the same way that we derived Navier-Stokes and continuity. We could do the same thing with the first law of thermo and get this guy, the conservation of energy equation, or the energy equation. So these are really the three fundamental equations that are governing our fluid properties and all the processes that are happening in the boundary layer. Let's non-dimensionalize these and see what groupings of variables are important. So if we non-dimensionalize conservation of mass, so this is the free stream velocity. Right, this is the characteristic length L, or in this example, the length along the plate. So I don't know why that keeps happening. Sorry. Someday I'll get this figured out. We would come to, if we plug that into the continuity equation that we had up there, we would come to this equation. So the continuity equation simplifies really nice. We can very easily get all our units out of it. Newton's second law, if we non-dimensionalize things in the same way as we did for conservation of mass, right, we could plug right everywhere. How we did this, everywhere we had a u, we plug in u star times u infinity. Everywhere we had a y, we plug in y star times L. We would get this guy. So we have a couple groupings of units on both sides. We have this guy here, u infinity squared over L. He's there and there. And then we have two different sets of groups there and there on the right-hand side. So let's get rid of the units. Let's get rid of stuff on the left-hand side. So we're going to do that first by multiplying by, so this gets rid of the left-hand side things. Right, we come to this equation here. So now our left-hand side is just u star, x star, y star, v star. Our right-hand side still has groupings of variables, but it has two kind of important groupings of variables. So this guy here, this guy here, right, u L over nu. This is nu. This is 1 over the Reynolds number. And this guy here, we actually have P infinity has units still, and that has units, so we can define a new dimensionless variable P star as P infinity over rho u infinity squared. And what that does is then gets rid of that grouping of units. Right, so we get this equation here that I have boxed, which is really 2D F equals ma. Right, it's Newton's second law. And the interesting thing we find is only depends on Reynolds number. And I'll just put an exclamation point on that. What that's telling us is that the important characteristic for fluid flow is really the Reynolds number. It's not, right, all of these things matter. The length of the plate, the velocity, the viscosity, the density, all of those different things. But if we have two fluids with the same Reynolds number, those will behave the same from an F equals ma standpoint, which is really interesting. Now let's do the same thing with the first law of thermo. So we'll start with this guy here in brackets. If we look at it, there are a couple different terms. This last one here is the term that physically represents friction heating. So if we have a fluid flowing over something, there's going to be friction in the fluid, and just like rubbing your hands together, that causes heating. It doesn't cause a lot of heating, and in many cases, it's approximately zero, right? Compared to other sources of heat or other forms of heating, it's approximately zero in many cases. Or many cases of interest. Right, this is how we do engineering. We assume away things that we don't like. This guy is challenging, so we assume it away. It actually is not a bad assumption. Right? We think about heat transfer, which is the class of problems more generally that we're interested in. We're usually driving heating or cooling in the system. We're typically doing that in some way. So we can say that that's the method that we're using is going to be more important than the friction heating. Okay. We're going to do the same thing where we non-dimensionalize things. We're going to use the same, then this is key, we have to use the same non-dimensionless groups or the same method for each of these three equations. So we still use, right, u is u over u star, v, the y component of the velocity, is v over v, u infinity. We have the x position, the y position, and our dimensionless temperature. And all of these are defined in the same way that we did before. We can write here how we're going to replace them in the equation above. Okay, if we actually do that, so if we plug these in, we get this equation. Sorry. And then lots of things start canceling out. Right? We can shift things around, move things from the left side to the right-hand side, and we get only this single group of constants. If we look at what that group of constants is, so that's alpha over L times u infinity times the free stream velocity. The Reynolds number is u infinity times L over nu, the kinematic viscosity. And the Prandtl number, which we just talked about last time, is the kinematic viscosity over alpha, over the thermal diffusivity. So really, this grouping of variables here equals 1 over the Reynolds number times the Prandtl number. And that's what we have written here in this equation at the bottom. Okay, that was a lot of equations. What's important? We'll talk about some of this in an example in the next video. But what we found was conservation of mass, conservation of momentum, and conservation of energy. Really the things that were important from a physics standpoint were the Reynolds number, right? That's kind of dictating what's happening in the fluid flow. The Reynolds number and Prandtl number, that's what's dictating kind of conservation of energy aspects. And for convection, the Nusselt number. So those are going to be our three groupings of variables that we are going to really care about when we're talking about the physics of convection. And we'll dive more into that next time. So that's all for this video. Join next time to, we'll introduce the concept of similarity. Bye.